let me discuss with you how to evaluate a surface integral over a cylindrical surface. Let me tell you how to evaluate the surface integral over a cylindrical surface. Suppose you are given a surface integral and you have to evaluate over a cylindrical surface. Let me draw a cylinder first. So see, this is a cylinder. Suppose I have to evaluate it. See, f is any vector function and I have to evaluate it over I have to evaluate the surface integral over a cylindrical surface. See, in cylinder, I'll tell you the best way of evaluating the integral over a cylindrical surface. You can use the earlier method also, like taking the projection of cylinder over xz plane or over yz plane. You can do that way also, but I'll advise you do as I am telling you, right? This is the best way of doing the surface integral over the cylindrical surface. Please listen very carefully how to proceed when you are asked to evaluate the surface integral over a cylindrical surface. See, instead of taking projections, let me take the element ds on the cylindrical surface. What can be the element ds on cylindrical surface? The element ds on cylindrical surface can be like this. This is an element over the cylindrical surface. I'll use different color. So this is the element ds on the cylindrical surface, right? This is ds. If I take the projection of this ds, this is see, what is this? What is this? Say this is equal to dz, and what this is equal to? This is equal to, if I take this as say theta, and if cylinder is x square plus y square equals to a square, if this is theta, what this will be equal to? This will be d theta, and this particular length is going to be AD theta. So if this is AD theta, this is also AD theta. So this ds comes out to be, the magnitude of this ds comes out to be AD theta dz. And what is n? For a cylindrical surface, n will go in radially outward direction. So what is n? See, cylinder, the surface cylinder is, mathematically it is written as, it belongs to the family of level surface given by x square plus y square equals to constant. So n can be written as like this, which is xi yj, and the magnitude is a. So this is your n. This is your n. So this surface integral will convert to f dot nds equals to f dot xi yj upon a d theta dz. So this converts to a double integral, and I write f dot xi yj d theta dz. Now you convert it to polar coordinate also. You have the f, you take the dot product and then do this integration, you convert it to polar coordinate. You write x equals to a cos theta and y equal to a sin theta over cylinder. On the cylinder, see, your x is a cos theta, y is a sin theta, right? Because the rho, see, in cylindrical polar coordinate you have three variables, rho, phi and z. So for a cylinder, rho is constant. Rho is a distance of any point from the axis, which is constant for a cylinder. Phi over here I have taken a theta, and z is also third variable. So we'll evaluate it. We'll convert this surface integral into double integral by taking a surface element on the cylinder also. Here I won't take any projection. I am taking surface ds on the cylindrical surface itself. I'll take one example and you'll see how this can be done. This is very easy, right? Once you understand this is very easy. You can do any problem which is based on surface integral on cylindrical surface using this. You take directly cylindrical surface, right? Draw this n is given by this, and ds is a d theta dz. This is a d theta, see curved surface, a d theta curve, length of the curve, a d theta, and dz. So multiplying this, you get the magnitude of ds, a d theta dz, right? N can be formed like this. So it can be converted into double integration involving the variable theta and z. If you have any x and y over here, you can just write x equal to a cos theta, y equal to a sin theta, right? And limit of theta will be, if you are given the whole cylinder, it will be 0 to 2 pi, and z will be from this base to this base. If this base is at z equal to 0, this is at z equal to a, it will be 0 to a or 0 to b if this is z equal to b, right? I'll take one example which will make it very, very clear. So let me consider this question, right? To make my point understand, I have taken this question. Evaluate f dot n ds, where f is zi plus xj minus z 3y square zk. So remember this is k, and s is the surface of cylinder x square plus y square equal to a square, along with the bases included in the first octant. So this is cylindrical surface plus the two bases which are in the first octant. Let me draw the figure first to make it clear. So this is the cylinder we are considering, x, y, z. The surface is this cylindrical surface and the two bases. Let me call this as S1, this as S2, and this as S3. So we have to evaluate the surface integral over S1 plus S2 plus S3. It's very clearly written. Along with the bases including the first octant between z equal to 0 and z equal to b. This is z equal to 0. This is z equal to b, and your S3 is x square plus y square equal to a square. Alright. Now, so we have to evaluate the surface integral f dot n ds, or say we have to evaluate it over S1 over S1 over S2 over S3. Now let me evaluate it one by one. S1 is a plane surface, it is lower base. So on S1 your z is 0 and your n is minus k. See, when nothing written, we take outward row now. This is k, this is minus k, n is minus k. So your f dot n comes out to be 3y square z, which is 0 because z is 0 on the lower base. So on S1 you find the integrand f dot n is 0. So f dot n ds on S1 comes out to be 0. On S2, here z is b, so n here is k. So f dot n comes out to be minus 3y square z, which is 3b y square. So on S2, f dot n ds comes out to be minus and S2, one more thing, S2 is a plane surface, so your ds will be dx dy only. It will be dx dy. Yes, it is dxdy only. And see, S2 is a circular, it's a kind of, S2 is something like this, right? Yes, this is S2, right? So I'll convert it to polar coordinate and we'll get r square sine square theta r dr d theta. R is varying from 0 to a and theta varies from 0 to pi by 2. So I will first integrate this r cube dr, which will become r4 by 4, and put in the limit, it will become a4 by 4. So this comes out to be 3b a4 by 4, and this integration 0 to pi by 2 sine square theta d theta. You evaluate this, it comes to be pi by 4. So this comes out to be upon 16, or better I should write 3 pi a4 by b 16. See, this is very famous integration. You must remember this. This is a pi by 4. You can use gamma function to evaluate this. Now I have to evaluate the surface integral on S3, which is very important. See, on S3 I can take this surface element, I can say this is theta and this is d theta, so this is ad theta, this comes to be ad theta, this comes to be dz. I'll rub the upper portion. So for this cylindrical surface, your n is, what is your s? S is this. This is your s. It comes to be xi yj upon a. Then your f dot n will be, this comes to be zx plus xy upon a. This is your f dot n. Oh, sorry. So we'll evaluate this. So on S3, your ds comes out to be a d theta dz. So on S3, your surface integration f dot n ds comes out to be double integration of zx xy upon a d theta dz, where I'll cancel out this a and a. Z is varying from 0 to, it is 0 to b. Z is varying from 0 to b. So this comes out to be, I'll put it as z. I can say x on a cylinder, x can be written as a cos theta, y can be written a sin theta. So this comes out to be a square sin theta cos theta d theta, or I write dz d theta, right? Let me first integrate with respect to z, and since only in one octant, theta will vary from 0 to pi by 2. So I'll get this, I'll integrate first with respect to z. So this comes out to be 0 to pi by 2. This will be z square by 2. So it will become ab square by 2 cos theta. And there is no z, so integration will be z. This will be a cube sin theta cos theta d theta. Or finally what you get is a sorry, this will be, this won't be, this will be, I've committed a mistake. So this won't be a cube, this will be a square b, right? So I'll take ab out, right? So this is pi by 2, this is b cos theta plus a sin theta cos theta d theta, which comes out to be ab b sin theta plus a by 2 sin square theta, and limit is 0 to pi by 2. So it is 0 to pi by 2. This will be b by 2, right? Sorry, this is b by 2. So finally what you get is ab a plus b upon 2. ab a plus b upon 2. So we have evaluated the surface integral on S1, S2 and S3 So finally what you get is, finally you add all the surface integral. So your surface integral is, now I write it, it will be the complete surface integral f dot n ds was the cylindrical surface on the two bases, which I write as S1, S2 and S3, comes out to be over S1 it is 0, and on S3 it is minus 3 by 16 pi a4b, right? Pi a4b, and then plus ab by 2 a plus b. So it is ab by 2 a plus b 3 by 16 pi a4b. This is your final answer. This is the final answer, right? So please do it like this only, right? You do it, you take, whenever you are asked to find out the surface integral over a cylindrical surface, you just heed to my advice, you do it by like this only. You take a cylindrical element, right? It is easier to do, it will be easier, and you can do every question on the surface integral on cylindrical surface, right? So you do like this only. You try other questions from the book also.